This is test number 6, starting with number 2. The figure shows equipotential surfaces. An electron is placed at B. Where's it going to go if you release it from rest? Well, the electric field is equal to negative dV dx, so that's good, and that means that the downhill direction is this way. The downhill direction from 15 to 10 to 5 dV dx would show you which way V is increasing. Negative dV dx shows you downhill. So the answer obviously is C. A lot of people said A, and I can see it's an electron. Electrons don't follow electric field lines. Electrons are negatively charged. Field lines show you the direction of the force and the acceleration on a positive test charge. Electrons are negative. Gotcha. Number 7. A spherical conductor of radius r carries a charge of plus q. A neutral conductor of radius 1/3 r, okay, let me draw those in there, brought into contact with this first one. The charge on the smaller sphere after the separation is closest to the charge on the smaller sphere is, okay, now why does charge flow? We just said that. Charge flows due to a voltage difference. Voltage for a sphere. Voltage is equal to kq over r. It's the same equation, similar looking equation for the voltage around a point charge. I'll never forget that. I'll tell you why sometime. Anyway, we have kq big over r is going to equal kq small over 1/3 r. And then you can rearrange, get rid of the constant. So 3 times q small is equal to q big. That means that q small is 1/4 q and q big is 3/4 q, because big and small together have to give you back your original q. Again, charge flows until the voltages, the heights, even out. Speaking of flowing, charge number 10, a voltmeter connected between T and S would have what magnitude reading? Well, looks like we have to analyze the circuit here quick. 1/5 plus 1/20, that's 4/20 plus 1/20 is 5/20, 1/5, 4. 4 ohms, okay, and then we can add up all those resistors. 4 and 2 and 0.4 and 3 and 0.6 makes 10. And then we can add up all the voltages. Uh-oh! Batteries put in backwards. We'll take clockwise to be our preferred direction. So we have 25 in the right direction, 5 in the wrong direction. Total voltage supplied by these guys is 20 volts in the clockwise direction. Total resistance is 10 ohms. And you know what that means. V equals IR. Total current, 2 amps. 2 amps in the clockwise direction. So now we can figure out the voltage drop across all those resistors. Voltage drops across all those resistors. This is a lot of work here. And notice that the 5-volt battery that's a negative 5 volt because it's a waterfall. You're dropping 5 volts there. The 25-volt battery is a positive 25. Can you add those up? Well, you can add them clockwise or counterclockwise. You're going to get the same 15.8 volts either way. Number 20. We got a region of space and electric potential is cylindrically symmetric. What? And described by the formula V of R is equal to negative CR squared, where R is the distance to the symmetry axis and C is a constant. So an electron, again, it's an electron placed at a point, a distance R from the axis, and which will be true. Again, we're looking at the electric field is equal to negative dV dx. Electric, time to take a derivative. You thought we were going to get out of here without taking a derivative, but we aren't, and you make it a negative derivative. Do you agree? I hope you do. So this means that the answer has to be E. The answer has to be E. Once again, the electron goes in the direction opposite the electric field. If R is positive, then the electric field will be positive, and the acceleration of the electron will be negative. So it'll always be accelerating back towards the origin. It'll oscillate around the axis. Tricky question on a couple different fronts. Here's the last one, number 22. 2 large isolation, conducting plates of an area A are separated by A, italicized A, distance D. The 2 plates carry charges plus Q and negative Q respectively. We're talking here about a parallel plate capacitor. Which of the following best describes the behavior of the electric field in the region between the plates and the potential difference between the 2 plates when D is increased to 2D, keeping the charge on each plate fixed? And here is the electric field For a parallel plate capacitor, a nice uniform field. The electric field will stay the same no matter where you are, close to negative, close to positive. The electric field has nowhere to go. People were thinking about the electric field around a point charge. That's a good electric field. Yeah, that gets weaker. Those lines spread out. For the parallel plate capacitor, you got nowhere to spread out to, so the electric field stays constant. There's one thing you know about a parallel plate capacitor, it's that the electric field is going to stay constant. Now what about voltage? Here's our equations. And we said that the distance gets bigger, so the capacitance gets smaller. And if the capacitance gets smaller for a constant Q, then voltage has to double, so the answer is C. A simpler equation, although one that's not really on the equation sheet, well, delta V is equal to negative integral EdR is on the equation sheet. And again, the electric field is constant, so the voltage difference between the plates of a parallel plate capacitor is equal to the strength of the electric field times D.